Thank you for joining us for today's webinar with Antennex and Electro Rent. We're very lucky to have Anouk and Mark from Antennex presenting today. They both have extensive industry experience with antenna measurements and RF characterization. Before we begin, I just want to remind people who we are at Electro Rent. At Electro Rent, while we don't make the testing equipment that engineers use, we do make it easier for organizations to procure and manage their test equipment. With an inventory of more than $1 billion and 11,000 product types, we carry test equipment from the top OEMs across the globe. Our global reach means that our inventory and our people are located where your people work. Electro Rent provides end-to-end solutions for the complete test equipment lifecycle across many industries, including those you see on this screen. Before I hand this over to our stars of the hour, Anouk and Mark with Antennex, I just want to remind attendees that if you have a question, please put it in the chat. And please note that we have set aside some time at the end of this session for Q&A as well. So take it away, Anouk.
Yes, thank you very much, Leon. And yeah, thank you very much, everybody, for joining. So today I will be introducing you a little bit about the Antennex product that we are currently having. Here on the slides, there's my name and my email address, and also the email address of my colleague, Mark van den Bosche, who will do the demos. So we will have a couple of things that we'll show you today. So indeed, first I will introduce a little bit about ourselves. Then I will focus on the features of the new product, show you test metrics and examples of where you can use it. Our product is very new to the market. It has very exciting capabilities and it is constantly evolving. So I'll be showing to you as well our roadmap of this year. And then later we will have the demos given by Mark with a wrap up and some Q&As. Now there's also going to be poll questions in between to have the session be a little bit interactive. Your answers are fully anonymous, so we cannot correlate answers with people answering them. So just so you know that, and it would be nice if you could answer those. So a little bit about us. Antennex is a company that, of course, makes antenna measurement systems. We have a long history of antenna measurements, mainly in anechoic chambers. And our niche is specifically testing integrated antennas, so where we have RF electronics and antennas working together. Now, for passive antennas only, anechoic chambers are really great, but when we start integrating them with RF electronics, the test cases, the number of test cases start going up, the types of tests become a lot longer because most of them start to be built around power-based metrics, which is more related to overall overall radiated or received power. And there, the anechoic chamber is very slow and sometimes difficult to operate as well. So we really introduced this solution that's based around reverberation chambers to cover those types of tests. So in our company, we have a unique combination of both antenna measurements and RFIC test knowledge. And now we are based in the Netherlands, but we have support in the USA as well through Electro Rent. And we're a company that's very proud to be completely run by antenna measurement and RFIC measurement people. So yeah, just to recap the anechoic chamber, of course, most of you who are here in this webinar will likely be familiar with it. But especially when we are testing about overall radiated or received power, that typically requires a full mechanical scan around a device under test or by moving the device under test itself, which can also be challenging, which leads to quite slow testing times when we are talking about those types of measurements. So we're talking 30 minutes to a couple of hours per test. And if you have many test cases, that can take take you definitely a week to characterize your device. So it takes up a lot of lab space typically. You need an expert operator to do the alignment well. You're probably very familiar of doing laser alignments and trying to get your DAT precisely aligned, which is what makes it, especially at shorter wavelengths, really sensitive to errors. So just because of that alignment, because of that setup time, because of the way that the measurements are done, these are some risks of using the anechoic chamber for all of your tests, just due to possible delays. So that is why we have introduced this new solution that's based around a reverberation chamber that you can use to offload anechoic chambers or to bring certain types of tests in-house that you cannot do because you just don't have the space or resources for an anechoic chamber. So this chamber performs most of the anechoic chamber tests, not all of them, cannot test a pattern, but everything that is power-based, which tends to be a lot of the metrics related to RF electronics, can be done in this chamber, and also in a much shorter time. So as you will see, we can do a TRP test in a couple of seconds, for example. And also, we don't compromise on the accuracy with this method. In fact, you are a lot more accurate by doing overall radiated or received power tests in this chamber than in an anechoic chamber, because those uncertainties are typically higher with the many corrections that you need to introduce. So it's also tabletop, so just fits on any lab bench. So the photo that you see here is on just your average lab bench. A big plus is that it doesn't require antenna alignment. I will explain you the principle on the next slide, but this saves you a lot of time and potential errors, and it has fewer moving parts, so it's much more reliable and less likely to break down. So here you can see the inside. So it's, as you can see, not an anechoic chamber. It's reflective and metallic on the inside. So it's actually the dual of an anechoic chamber. So how does it work? Instead of scanning around a device to get the total radiated power or received power, this chamber changes the electromagnetic environment. So that's basically equivalent, but significantly faster and with less margin for error. So if we have so if we place the device in another position of the chamber, again, we change the environment, so we get the same result. Now, this chamber has been specifically adapted for higher directivity systems. So you can see the pyramid on the top and the shape of they're called mode steering mechanisms. They're in the back right and on the top left, and they are used to change the environment. And the pyramid is optimized to reduce direct reflections to your device under test, such that your device will be in a similar operation as it would be without the chamber in there. And then there's just a single probe that picks up the signal or injects the signal into the chamber. You can see it on the slide on the right. There's an open-ended waveguide that is connected to a feed-through. So you can see that on the picture on the bottom left, and that is connected to an RF detection system such as a vector network analyzer, a spectrum analyzer, and oscilloscope. Now, inside of the chamber is a computer that controls the chamber, but also controls the instrument. So you can put the settings on the instrument, so there's no need to write skippy commands. It's just plug and play with an Ethernet cable, and then you can control it from the graphical user interface on the screen, or you can control it remotely with your laptop using our API, and you can also automate your measurements in that way. So this solution in this way is really exclusive to Antennex and protected with patented knowledge and algorithms. Again, this chamber is just a lot faster just because it uses a different technology than anechoic chambers, and it can really help, especially integrated antenna development. So I would like to go to the first poll question. So what type of chambers do you use for antenna testing? So we can go to the poll now, Leon. So your options are if you're using anechoic chambers only, if you're only using reverberation chambers, both types of chambers. Maybe you don't perform antenna measurements and you're just here to learn, or another option is also possible. So I'm just going to give you a little bit of time to answer the questions and submit it. Look. Okay, so that is very interesting answers from our audience here. So none of you actually use reverberation chambers. So yeah, it would be good to explain you a little bit more about that. But definitely, especially if you're mainly using anechoic chambers, some of the issues you would probably be familiar with, and it might be beneficial for you to switch some of those tests to reverberation chambers because they're naturally better at testing those types of metrics. All right, so let's go back to the slides. Great, perfect. So thanks a lot for your patience, everybody. So yeah, here are some features of the chamber. We call it the wireless connector because it is basically the equivalent of a coaxial connector in many ways, or an RF probe, because we can test overall power radiated or received in a perfectly matched environment, where the matched environment is the air. So the frequency range is 5 to 170 gigahertz. The chamber in metric sizes is 80 by 80 by 80 centimeters, and the device under test size that we can support is about 30 by 30 by 30 centimeters, or in imperial about a foot by a foot by a foot. So again, it's really easy to set up just because we already have that compatibility with many instruments. It's tabletop. We've set this chamber up, taking it out of a van into a lab in less than 20 minutes. But also the positioning of your antenna is done instantly and doesn't require laser alignment. And again, it's accurate. So it can be controlled on chamber with the GUI or with remote control with the API. We have compatibility with Keysight, Rohde & Schwarz, and Tektronix instruments. We typically check what instruments you have in your lab to make sure that they're compatible, such that you don't spend time writing skippy commands. And with the purchase of chamber, support is included from our side to help you set it up in your lab, or if you have any questions while operating it. So where can you actually use it? So we are active in a couple of different markets. The wireless or telecom sector can use it for some applications, automotive sensing as well, aerospace defense, education, EMC, and others. And especially the first three, I'm going to go into in a little bit more depth with some applications and use cases. So where in the cycle of your organization can you use it? We have people using it in research and development, where we control the chamber to have the most accurate measurements. I'm not sure if I said this, but it's based on an averaging principle. So the longer we run the test, the more accurate we can get it. So you can use it there to really push the components to the edge of their abilities and to optimize your data as far as possible in research and development. Then also in characterization validation to test it for as many use cases as possible for many different modules to validate your product, but also in production for very quick checks of your devices. You can use it too, especially in aerospace defense, where the number of modules that need to be tested may be lower, and it can still do manually. That's as well where you can use the product, and also in post-tech support and RMA. There it's also useful because really anybody can operate it. You don't need an experienced metrologist to find and debug problems very quickly, whereas in an anechoic chamber that may be difficult because there are many other errors that can be introduced to the measurement that may be related to an operator, and then you're not sure if it's the device or the measurement. So let me just go into the first three markets in a bit more in depth. But first we have a poll question. I'm interested to know in what activity you are mainly involved. If you're mainly in R&D, characterization, validation, production, RMA, post-tech support. Great. Okay, so we have a bit of a mix of many different options. I'm curious the 80% other what that is. If you are willing to communicate that, that would be really helpful. But indeed, it seems most of you are in R&D. But as well a percentage of you in characterization, validation, and production. And your answers really help me to make the webinar as valuable to you as possible. So thanks a lot for replying here. So let's go back to the slides. So then I will highlight a couple of cases in the wireless and telecom industry. So again, the chamber tests basically everything that's related to power spectral density or total radiated or received power. So there on the left side, you can see a couple of cases where you can use them, such as point-to-multipoint communication of phased arrays, user equipment. You can use it to test phones, watches. You can use the chamber for that. Wireless interconnects for near-field communication. Fixed wireless access, ultra-wideband testing, and as well joint communication and sensing applications where sensors are maybe integrated with your telecom device, and as well SATCOM modules too. So on the right-hand side, you can see a list of types of tests that you can do. So again, just TRP testing in Alpha 2 for different beamforming settings of phased array. You can use this to 6G proof your lab, especially there because antennas and RF electronics are getting closer. So you're going to want to be testing more power-based metrics and to debug it there. So that's some place where you can use it, especially in R&D, to match the antenna and to have the active antenna be as efficient as possible for the best settings that you can use. That's where you can use it as well. Same with algorithms, antenna efficiency. Well, you can see a couple of more use cases here, especially ultra wideband, maybe a very interesting one for you too, because it takes a while to do pre-compliance testing in anechoic chambers. Here you can test the power spectral density a lot quicker. Then we have some applications for automotive. So we have a dedicated application that will be releasing this quartile. So I'll be also showing that. So you can use it for ADAS applications in both 78 and 140 gigahertz bands, especially in 140 gigahertz. Our chamber may be quite interesting for you because there many people are making more packaged antennas. So with the RF electronics and the antennas even more integrated and close to each other. So again, for those cases, that's where we see the value. As well as vitality sensing for in-cabin and also indeed anything related to FMCW radars or ultra wideband we can test. So different packagings, different radomes, and especially for those who click production, if you're in production related to radars, the application that we have can test TRP of a radar with the time using the information of just one single chirp sequence. So that can be incredibly fast there too. Then in aerospace defense, again, we are also seeing high levels of integration to get the optimal performance out of your system. So again, SATCOM, AMSO applications, hybrid communications, and radar, detect and avoid systems, and also sensitivity to jamming. These are some applications that we can test. And on the right-hand side, you can see where you could possibly use it. So to test PA saturation levels for either communications or indeed burst type of signals or pulse burst type of signals, linearity of your SATCOM module, sub-module or full module testing as well, out of band susceptibility or out of band radiation, such as from your LO, you can check as well. So here's just a list. Anyway, if you have questions, just make sure to put them in the chat and we'll make sure to answer them at the end. But also, if you're wondering if a specific application works for our chamber, we'd be really happy to set up a specific meeting with you in the upcoming weeks after this webinar. So again, a poll question, what frequency range are you mainly active in? Is it mainly the sub-6 gigahertz or any of the other bands here? And I think this one also then has the multiple option possibility. Very interesting to see these results. So a lot of you are working in the sub-6 gigahertz, but also a few of you above, especially the more than 90 gigahertz. Definitely make sure to set something up with us, because in those cases we are seeing very high levels of integration, also in E-band as well. And we'd love to see how we can chat with you to see how we can help you. Similar as well to the 6 to 15 and 15 to 60. If you don't have a separate antenna and you integrate your antenna with your device, that could be interesting too. We can go back to the slides. And then just a word for the sub-6 gigahertz. So again, our chamber starts at 5 gigahertz at this point. That's from where we've spec'd it. But we are definitely taking your feedback related to sub-6 gigahertz into account to be able to make solutions for that as well. So these are the test metrics that you can test. So again, most of it's based around power spectral density or total radiated power, or perceived or transmitting. So you can test your power gain, compression points of your device, intermodulation products, ACLR, adjacent channel leakage ratio, out of band emissions, power outlet efficiency or drain efficiency if you combine it with your DC supply, especially in our API, you can do that. So that's for transmitting, and receiving, it depends on your device. If you have an IF or RF output, it's basically the same. If you have internal ADCs, you can synchronize that with our API to make sure that we can do the test in that way. So indeed, receiving depends on what type of device you have, and in transmit we can just treat it as an unknown box. And on the right-hand side, you see some examples. So these are some typical speeds and corresponding uncertainties. These tests were done at 60 gigahertz. So you can see that we can do a single frequency power at or in a band of about a megahertz, depends on the resolution bandwidth of your spectrum analyzer, in a few seconds with a very low uncertainty. This is 2 sigma, the measurement. Now this uncertainty is what corresponds to the operation of our chamber. So if you have other instruments that you add to your setup, that of course adds the uncertainty and your device under test itself as well. But here are just some examples such that you have some ballpark figures, and we'd be happy to explore with you how these numbers are when you have your device under test. So a little bit about our roadmap of 2025. In Q2, we will be releasing an FMCW radar testing capability, and in the end of the year, we're releasing a noise figure capability too. And we're constantly adapting and taking your feedback into account. So next slide. So just to quickly show you on the next slide, the FMCW testing suite. So again, this will be released very soon. There you can get a full spectrogram of the measurement, so the time versus frequency to get chirp linearity, chirp rate, also total radiated power and power spectral density. Especially total radiated power, we have a possibility for that to test that again within the time it takes to send your burst of chirps out. So if you're interested in that, especially for production, feel free to contact us to learn more. And then we're also introducing a noise figure capability to the chamber, where we can use it as a wireless noise source with tunable ENR, such that you can do your Y factor measurements in the same way as you would do in a conducted way, but now you can do it with the antenna there to get a good representation of the noise figure when you have your antenna as part of your system, because it will change its behavior. And then I would like to give the word to Mark, who's going to show you a couple of demos of the operation of the chamber. And here you can see him in our lab in front of the chamber.
Yes, thank you, Anouk. Welcome everyone in our lab. And I'm Mark van der Bosch, and I will take you actually through 3 demos. I will show you how easy it is, in fact, to use the chamber, the wireless connector, to do a power spectral density measurement, a power spectrum. It's as easy as actually using a spectrum analyzer. Then I actually will come to a very nice feature where you can do very fast measurements of a TRP in seconds, just at one single frequency. And then finally, we will show you how easy it is to integrate the capabilities into your platforms, test platforms. That will be the final demo. But first, I will take you to the chamber, which is behind me here, to give you an overview of the setup. What you see here is the wireless connector, and the heart of the wireless connector is, in fact, this chamber, the reverberation chamber. But outside, there will be external instruments, and these instruments can be like a spectrum analyzer, a network analyzer, and also an oscilloscope. And the choice depends a little bit upon the type of applications that you want to do. At first, let's have a look what's inside this chamber. So for the moment, we have been putting in one device under test, which is a phased array device, which is being fed by some bias and some USB control. So there is no RF going in here, just the state is being controlled by the USB. And then here, there is the phased array architecture that allows us to transmit and to receive with the device under test. This is a commercial available phased array system. We can put this device in the chamber at almost any location. And that's very handy, of course, because you don't have to worry about alignments in contrast to, for example, the anechoic chamber. Now, what's important, though, is that the direction of the radiated fields is upwards to the ceiling of the chamber. Why? Well, we want to avoid direct reflection. to that device under test. And the top of the chamber has been designed specifically to minimize the possibility to get a direct reflection. And in fact, between a steering angle of -60 to 60, that direct reflection should be avoided. So that's a kind of an important thing to take into account. Now, how are we bringing in the DC and how are we bringing in the USB control or any other type of control? Well, on the side of the chamber, there are panels. And I do have an example here of a panel. And you can see here the outside. For example, here you have some waveguide. If I open this, you have a USB connection of this panel. There are coax connections, BNC connections and coax connections. So you can feed in RF into the chamber, or you can basically measure the fields inside the chamber by bringing the RF outside. So there is a lot of flexibility in the configuration of this panel. So we have one of these on the side of the chamber. Now, the device is radiating or receiving fields. Now, you need, of course, something that is either measuring the fields or generating the fields. Well, on the side also, we do have reference antennas. And these antennas are being provided with the system. And depending upon the frequency bands that you want to measure, they will be different. And they're coming out on the side panel. And here you have an example of such a panel. So in this chamber, in fact, we do have these two types of antennas. And on the side, you basically have a waveguide and you have an RF connection. So this allows us then to connect the external equipment. And you can see here we have been connecting a Rodian Schwarz spectrum analyzer as the receiver, because we will be using the device in this case for radiation and not for receiving. Now, besides that, we also have stirrers in the chamber. Why? Because this is a metallic chamber, so we will have standing waves. And we want to create actually a uniform field in the chamber by doing some averaging techniques. And to create that uniform field, you need to stir these waves around. And for that, there is a vertical stirrer, and at the top, there is a horizontal stirrer. And they can be used in two modes. They can either continuously stir, and we can do some sampling of these fields and process them, or we can actually step the stirrers and per step measure the fields and then process them later. Now, when you are going to measure with a spectrum analyzer, you also need to do a additional calibration. Why? Because the device under test by itself, even when it's not active, is going to change the loss properties of that chamber. And to characterize that, there is a calibration module foreseen in the chamber on top that allows us to measure the difference between factory cal and, in fact, when you are putting in that device under test while it's inactive. As soon as that calibration is done, at that moment, you also need to take into account the type of antenna you're using as a reference antenna, and you need to take into account the coupling to the spectrum analyzer. So let's come to the outside. So the nice thing of this chamber is that actually it has a computer. And because of the fact that it has a computer, we are able to have a user interface on the system where, in fact, interactively we can do the different types of measurements supported by this chamber. There are different applications supported. For example, power spectrum measurement. We have a FMCW type of measurement for radar applications, and the number of applications will grow in the future. So interactively, you can work with the interface. But that's not all. The instrumentation on the site, in fact, is totally invisible. Once you made the connection between the chamber and the instrumentation, you are ready to go, and you only need to use the interface that is being provided over here, and the type of equipment is totally hidden for the user. Now, I can imagine that you also have your own characterization plans and test plans. Maybe you're using MATLAB, maybe you're using Python or something else. And you really would like to integrate the capability of this chamber in these test plans. Well, this is pretty fluently because there is a remote control capability of this system that allows you to easily access the capabilities of the system, set some parameters, do some measurements, and so forth. And the nice thing is, also there, the external equipment is totally hidden for you as the user. So this concludes a little bit the overview of what is the wireless connector and how does it look like and what does it contain. So now that we had an overview of the system, we actually will go to the first demo. And in the first demo, I will be showing you the power spectral density measurement and a power spectrum measurement as simple as a spectrum analyzer. And it's going to happen on that device under test that I just showed you, which is a 60 gigahertz phased array antenna. So let's now go to that demonstration. Here we will show how to do a power spectrum measurement of a device under test. That means power basically as a function of time. And the system has been calibrated before. And the next step that we need to do is typically for a power spectrum measurement of for a radiating device, the reverb chamber has stirrers inside. And the stirrer mode that we typically select for power spectrum measurements is the stepped mode. So there are two modes, step mode and continuous mode. Step mode means that the stirrers will be put to a certain position and the measurement will be done. Then a next position will be taken and a measurement will be done. And then, in fact, you're stirring the fields in the chamber. And at the end of the day, when you collect all that information for the different stirring positions, applying some averaging to that, you in fact get a field, an average field that is pretty uniform across the chamber. And that makes the measurement very independent of the position where you are putting the device under test. So here I will go into stepped. I'm going to use the default settings. And there you can see that for the positions, there are 10 positions for the horizontal stir, which is positioned at the top here. And then in the back, there is our vertical, it's a vertical stir that also has 10 positions. And we are doing, in fact, steps of 5 degrees each time. And then for each setting, in fact, the spectrum analyzer is going to measure the power spectrum and then all the data collected. And there is some averaging applied at that moment. Now, the spectrum analyzer here, we are not doing anything specifically on the spectrum analyzer. Just the default settings are being used, driven by the software in the reverb chamber. Now, of course, we must make sure that we define the span across which one we are going to measure. That span needs to be a subset of the span that for which we calibrated, because otherwise we will mix some certain measurements that's not calibrated and calibrated. So we need to make sure we are within that span. And here I'm going to select 62. So we have a radiating phased array antenna at the moment configured in the system. And it's radiating around 62.6 gigahertz. So I'm going to take a span here from 62.3 gigahertz to 62.9 gigahertz. So we have a 600 megahertz span that we're taking at this moment. And then I'm actually going to measure. And on the screen, you see the noise floor, and you see one spike moving up and down. So we are radiating at one frequency. And the nice thing of this approach is that very quickly, suppose you have LO leakage, suppose you have spuriouses, they also will show up within the span for which you were collecting the measurements. So it allows you to very quickly get insight in the behavior or in the abnormalities of the device within one power measurement, basically. And just imagine that you need to do that in an anechoic chamber. And here you do have the result. So you can see, in fact, that this is a nice device. We see the noise floor. And then here we have one nice spike at the frequency at which it is radiating. So this is the total radiated power provided by the device at that frequency. So this gives you a quick overview of how you can do a power spectrum measurement as a function of frequency. Okay, so now that we know how to do this power spectrum measurement or power spectral density measurement, in many cases, when you are analyzing or diagnosing a phased array, you're not interested in a frequency sweep, but you want to fast change the states of your device under test, and in a fast way also measure the total irradiated power. And there we will use the unique capability of the zero span of a spectrum analyzer. So let's now move to the next demo.
What we will show now, after doing a power spectrum measurement as a function of frequency, and you see the results still on the screen, we will now do a zero span measurement, that is at one fixed frequency. Now, why would you do that? Well, in many cases, when you want to investigate the proper functioning of your phased array, you would like to control different elements, different like gain settings, different phase settings. And it doesn't make sense to do really a frequency sweep. Typically, you want to do that at one frequency, and you want to do that as quickly as possible. So we will use the zero span capability of the spectrum analyzer to actually measure the power as a function of time. But as we are measuring the power as a function of time, we will have the stirrers continuously running so that in fact we are sampling in a random way the fields presenting to the reference antenna. And out of these calculations, in fact, we can then get the total radiated power at that given frequency. And we can repeat this, of course, for different state settings of the device under test. So how do we go from a power spectrum measurement to a zero span measurement? So first of all, we need to tell the reverb chamber that it will have to use the continuous mode. So we can push here, continuous mode. Now for continuous, there is no stepping of the stirrer, so we put it to value 1. And then there is continuous speed of the stirrer number 1 and continuous speed of the stirrer number 2. The values, the default values are 30 and 28 rotations per minute. These are typically good values for doing a random sampling of the zero span setting of your spectrum analyzer. Now, the zero span setting of the spectrum analyzer is a specific mode. And of course, you can tweak and tune that a little bit yourself on the spectrum analyzer. So it's what we call an advanced setting that we are using with the reverb chamber. And before we have been configuring the zero span mode on the spectrum analyzer, and we do have an application note that tells you or that explains you what the kind of preferred values are depending upon the type of measurement and the type of accuracy that you want to achieve. Now, once that is done, this preset state of the spectrum analyzer can be saved. And you see here, in fact, we have a limited list. We have the default value and we have a zero span configuration. That's being created before. And here you see in the menu like save, refresh preset list. That allows you to really do your own setting on the spectrum analyzer and then make it available to the reverb chamber software. So we put the reverb chamber in continuous mode. We have zero span. Now we need to tell the system at what frequency to measure. And the device we are having in the system is a phased array radiating at 62.64 gigahertz. So I put start and stop frequency to the same frequency. So 62.64 gigahertz, zero span. And now, in fact, we are ready to measure. So now we start the measurement. And when you look on the screen, then you actually see that you have a time varying power as the stirrers are moving around. And that data is being collected. And in fact, we already have the result here, where we have, of course, one dot on the screen because it's one frequency. So that gives you an idea about, okay, how can we pretty quickly get an idea about the behavior of a phased array for one frequency. Of course, now I can change the state of my device manually, for example, and then I could do a new measurement and have a look at what's going on.
Okay, so these measurements basically were done through the interaction with the graphical user interface on the wireless connector itself. But in many cases, you actually want to automate the process, for example, of changing the state of your phased array and then being able to do a total radiated power measurement. And that's what we will show in the next demo. We will see a graphical user interface in a Python program, which is a total separate program. Actually, it's very easy to create. I was able to create that program in less than a day with the graphical user interface, interacting with the reverb chamber to be able to capture a total radiated power as a function of beamforming. But let's go to that demo now.
So here we are connecting to the device under test, and we are connecting to the reverb chamber. The device under test, which is a phased array, is initializing for transmit mode. And once it's connected, we can actually go to the measurement tab, where you can see it's radiating at 62.64 gigahertz, and where we're going to scan the beam from minus 40 to 40 degrees, as it is a phased array, a radiating phased array. And we will make the steps in steps of 10 degrees. We start the radiation of the device, and then we are initializing the measurement. And what you see on the plot now is in fact the total radiated power as the beam is going from this minus 40 to the 40 degrees. And it gives you directly an idea about the quality of the device, as you would not expect that the TRP is changing radically. We stop the radiation, and in fact we finished the measurements.
So as you could see, one scan basically, or one measurement, one TRP measurement is only taking a couple of seconds. And then on the plot you were seeing on the x-axis basically the degrees for the beam forming, and then of course the total radiated power was the y-axis. So what you saw, in fact, was a graphical user interface built on Python. As I said, it's not a regular part of the Antennex software. It's just an example as what you could do also from your side. And what I was using is actually, I was using the high-level API that is being provided by the wireless connector. Now, in case you really would like to take control yourself of the lower level, for example, you want to control the stirrers yourself, that's also possible. So we're also foreseeing a low-level API. Actually, we are curious about the type of test platforms that you are using, so that we could make sure that we are covering a large amount of the platforms that are being used out there in the field. And for that, we do have a poll question here, a final poll question about the type of test environment you use. So you have a choice between the MATLAB, Python, LabVIEW, and maybe you're using .NET, or maybe specifically you're using C++, C. So apparently MATLAB Python is a par here. Apparently also we have a couple of people using LabVIEW, and then indeed the .NET C, C++ is less used apparently. So that's quite useful information for us for our future development. Thanks very much for answering the question. And now I will give the word back to Anouk.
Yes, so thank you very much for joining the webinar so far and listening to the demos. I did notice we didn't give the other option here in the fourth poll question. So if you have any other requests, don't hesitate to reach out to us. So also, again, the software that Mark showed in the last demo was something that he wrote himself in a day while using the functions of the Antennex API. So you just have the option to fill in those functions into your own program for controlling your DUT. So we did skip over the slide that was before this poll question. So if we can just show that real quickly, that you have an idea of what it looks like. These are just some of the functions that are, for example, built in the API. So again, high-level functions to just do a full measurement with a certain setting. But again, also low-level for you to control everything, especially if you know how this instrument works. Let's go towards the Q&A. So already one of the questions that came in was, can it measure the pattern? And the answer is, as I mentioned before, oh, it's getting dark here, is that no, we cannot measure the pattern, unfortunately, but we do test everything that is power-based. So everything that you can see that would take you a long time in an anechoic chamber, you can offload those tests in our system to do it a lot quicker. So that's one of the answers here. If you have more questions, just put it in the chat and the organizers are relaying them to me. However, maybe some other questions that you may have or that you would maybe think of this system is again how to do the calibration. So we need to calibrate the chamber loss out, which is about 20 to 30 dB. We have to do that with either a calibration module that we supply, which is a swept signal generator, and that can just work with the spectrum analyzer you were going to use anyway for your test, or we use a vector network analyzer. So if you have a vector network analyzer in-house for the calibration, you can do that too, and you only need to calibrate it for the type of DUT that you decide to put in. So that really only depends on the materials. Then something else that you might wonder about is the dynamic range of the system and of the instrument, which relates to mainly the equipment that you decide to use with it. So you saw in a demo a noise floor that might be a little bit higher. That was because the resolution bandwidth was 3 megahertz. We had to put that a little bit wider because the DUT was drifting. So to properly capture the radiation, we had to put it wider, which of course raises the noise floor on the spectrum analyzer. But again, we can go to levels as low as the noise floor plus that chamber loss. So if you have an amplifier after that, or if you have a sensitive test equipment, we can measure that. Yeah, the last part, which already what I mentioned, was about the chamber loss. Again, it's a lot higher than you might think, especially if you are wondering how much power returns to your DUT. That's about, and the loss is about 20 to 30 dB. So what returns to your DUT is about the total radiated power minus that amount, which is in most cases less than the mutual coupling. And I look very much forward to having a conversation with you in the future.
All right, Anouk and Mark, thank you so much for a very insightful presentation. We're very proud to have this exclusive product available to our customers. Thank you very much.